Hey, today is lesson 2.3. Obviously I'm out today. Hate that I'm not there with you all, but we're gonna get through this lesson together. All right, 2.3. So we have been talking about finding locations in distributions. So today, what we're going to talk about or normal distributions. Now, keep in mind, we can't use the mean and the standard deviation if we have right skewed, left skewed, if we have any type of outliers. We cannot use the mean and the standard deviation. We can use the standard deviation when things are roughly symmetrical and there are no outliers. Okay. That whole concept of being roughly symmetrical and no outliers is called a normal distribution. Okay. And so when we have a normal distribution, that makes things great. That's also the reason why we would want to identify outliers, because if we remove those outliers, if we remove it from our data set, now can we have a normal distribution? And if we have a normal distribution, there's so many things that we can do to run research and find out information and potentially apply it to the entire population. Okay. So we're going to do density curves and normal distribution. So we are going to use the density curve as a model of distribution of quantitative data. Now, right now, that probably doesn't mean anything, but you'll understand what I'm talking about here shortly. We're going to be able to identify relative locations of the mean and the median from the distribution of a density curve. So where is that mean and median located? And then we're going to be able to draw a normal curve to model a distribution of quantitative data. It's kind of like, this is like a standard. So if your data presents in a certain way, you can use this as a standard and get close. We're not going to be 100% accurate, but we can get pretty close. Okay. So we have just been exploring a single quantitative variable. Okay. And again, we have done a dot plot, we've done a stem plot, we've done a histogram. And we've been talking about this overall pattern. What's the shape? Is it, unimodal? Is it bimodal? Does it have like three peaks? Does it have gaps in between? Does it look roughly symmetrical with one peak, roughly symmetrical with two? Is it right skewed? Is it left skewed? Where's the center? Where's the mean? Where's the median? What's the variability? Like that's the range. We can do the variability as far as range. We can also start talking about standard deviation, IQR, things like that. We can do that IQR times 1.5, add it to Q3, subtract it from Q1, and we can identify outliers for a fact. Like we know for a fact that's an outlier. Okay. You've been able to take your StatMedic or your calculator and you've been able to find the mean and the median and also standard deviation. We can go and do max minus min and find the range. We can do Q3 minus Q1. We can find the interquartile range. Okay. So we're going to add one more step to this. Okay. When there's a regular overall pattern, we are going to use this simplified model called a density curve to describe it. Okay. So if we look here, okay, here's going to be our example. We've got this girl, Selena, and she works at a bookstore at the Denver airport. And she takes the airport train from the main terminal to get to work every day. Now, the airport just opened up, one of those skywalks you get on. It's like an escalator, but it's just flat. So there's a walkway that would allow her to get from the main terminal to the bookstore in 4 minutes. And she's kind of wondering, what's going to be faster, walking or taking the train to work? Okay. So here's a dot plot. Okay. And so what she did is she kind of did her own research study. She started recording how long it took her to get to the bookstore by train for each of the last 1,000 days that she worked. Okay. And again, we know it's going to be 4 minutes walking. So we're looking at the train time. And so here's our dot plot for it. So what percent of the time did it take Selena 4 minutes or less? Because you got to think for the train to be better, we need to have a significant amount of train time being 4 minutes or less, or it's just better for her to walk. It's probably better for her to walk anyway, because then she gets exercise. But okay, now counting all these dots would make anybody's head spin. I mean, it's crazy because, like, when I look at it, I'm gonna be honest, I see flames going up, I see curves. Like, what line is it in? I mean, this just looks like a nightmare to count. Okay. So is there not a simpler way that I can do this without going 1, 2, 3, 4, 5? And again, I'm not even sure, is it on 2.0, 2.1, 2.2? I don't know. I don't know. So yes, there's a simpler way. So we are going to use this density curve. So if you look, that shape with the dot plots looks roughly like a rectangle. So let's make it a rectangle. This is our density curve. Okay. And so we are going to use, we got the red shaded area under the density curve to approximate the proportion of red dots. Okay. So we're approximating this because we don't have to be exact. This isn't a life or death situation. We just need to know a good approximation. What's faster, walking or the train? Okay. Let's just be real. So now we have drawn this density curve. Notice the height here. We have a height of 1/3. Okay. So you got this height here of 1/3. Where did that come up with? Okay. Now we also look at here, the rectangle under the curve is between 2 minutes and 5 minutes. Okay. And so I want you to look 2 minutes and 5 minutes. The difference in that is 3. And notice that 3 is the denominator over here. Okay. So basically, if this was a 4, what do you think your height would be over here? It'd be 1/4. If this was a 5, what would be your height? Your height would be a 1/5. So real simple. You just have to memorize that. Whatever the range, whatever the length is, it's 3 units, my height will be 1/3. Okay. So that's going to represent 100% of the observations. Now, again, if you ask me, why is it 1/3? I'm going to tell you, because the book told me to. I don't care why. If it has a width, if it goes from 2 to 5, subtract that. If the range is 3, then your height is going to be 1 over whatever that number is. Okay. So here's some of the properties of this density curve. It's always on or above the horizontal axis. It has an area of exactly 1 underneath it, because 1 would be the same thing as 100%. Okay. And then the area under the curve and above any intervals of value, all of this is going to estimate. That's a huge word there, estimate. I'm going to underline it. The proportion of all observations that fall in that interval. Again, this isn't life or death where we have to be 100% accurate. I just need to know, about, 75% of the time, it's faster to take the train. Okay. But if you told me, around 10% of the time, I'm probably going to walk. So now let's compare this density curve to Selena's actual. Somebody actually went and they counted all the dots. Okay. Good for them. So on this dot plot, somebody counted 669 dots of all the 1,000 dots. Okay. And this is where, when she took the train, it took less than 4 minutes. Okay. And so if we did 669 divided by 1,000, we get 66.9%. Okay. Let's go over to the right of this density curve. Okay. So if we look at this density curve, you can see if we go from 2 to 4, there's a difference there of 2. Okay. So the red, this is all the train times, okay, that it took less than 4 minutes. That's why we have red and blue. Red is all the train times it took less than 4 minutes. Blue is all the times it took more than 4 minutes. So if we find this width here, 4 minus 3, or 4 minus 2, sorry, we get 2. We multiply it by this height of 1/3, we get 2 divided by 3, which is 66.7. Look, y'all, we're only 0.2 off. 0.2 off. So is she better off taking the train? Yeah, more than half the time the train is less than 4 minutes, less than walking. Now, I'm even going to be even further real with you. Like, I can almost look at that. If you look at the dot plot, I'm gonna go, there's a whole lot more red dots than blue dots. It's definitely more than 50%. Yeah, I probably don't need to do the math for me to make this determination in real life, but this is a stats class. So this is how we're going to do it. Okay, we've got to do the math. But yeah, she's probably going to turn around now and say, I might as well just take the train, because more times than not, it's ended up being less than 4 minutes. And even if I go over here, I mean, let's use some common sense. Like, 1 minute more? What's 1 minute gonna do? Yeah, let's be, I'm probably gonna take the train unless I need, to be walking and need the exercise, and yeah, probably not. Okay, so let's look at another example here. Okay, so we're gonna use an app or a calculator, and we're gonna generate a random number. Okay, we want to produce a number between 0 and 4, and yes, that can include decimals. So this random number generator, they all are like this. They're going to spread out its output uniformly across the entire interval from 0 to 4. Okay. And we're also going to tell it that you can generate a long sequence of random numbers. Okay. So what the book's asking us to do, draw a density curve to model this distribution of random numbers. Be sure to include scales on both axes. Then what percent of these randomly generated numbers will be between 0.87 and 2.55? Okay, maybe somebody's wanting to know. And then they want us to find the 65th percentile of this distribution of random numbers. So remember, at the 65th percentile, that would mean 35% of the data is above that number. Okay. So let's look at A. Okay, we're going to draw this density curve. So we know it's from 0 to 4. Okay, so that's going to be our range. You see that down there, 0 to 4. Now I'm going to draw a rectangle. I'm going to do the rectangle first. You see this up here. I got this line up here up top. Well, since the difference here is 4, okay, 4 minus 0 is 4. That means my height, I take that 4 and I just put it right there in my denominator. So the height is 1/4. Okay, got to label that. Okay. Now, what percent is going to be between 0.87 and 2.55? So let's look at that. So we're going to put 0.87 about where it's at, 2.55 here. So we need to find what the area is of this. Now remember, this is like a rectangle here, okay? We drew this down, it's like a rectangle. So we want to know what's the area here. Now go back to geometry. What is the area of a rectangle? We would do length times width. And 4 times 1/4 gives us 1, which would be 100%. Okay? It's kind of why we do that. Why the height is 1/4. So now what we're going to do is we're going to find the difference between these two numbers, 2.55 minus 0.87, and multiply it. So this is length. Okay, this is your length, and this is your width. Finding the area of a rectangle. Okay, length times width gives us 0.42. When we multiply this by 100, don't we get the percentage? 42%. So it's really kind of cool. Okay, what percentage is between 0.87 and 2.55? 42% is going to be there. Okay, yeah, pretty simple. Okay. Now, percentile, let's look at the 6th. Percentile is going to be what percentage of numbers, or what number is at the 56th percentile, okay? So 65% will be lower than that number, 35% will be above, okay? So if we wanted at the 65th percentile, then that means 65% of the data will be below whatever the number is. And again, this is X because I have no idea what that number is. But I'm solving for that number. What number has 65% of the data below it? Okay. And we know this area. Area is 0.065. So remember, area equals, this goes back to geometry. Gosh, probably even before geometry. I mean, y'all been doing length times width since middle school. Now, let's put put in our numbers. It says height here. I say it's width. So area is going to be what? 0.65. Oops, I kind of wrote over that. 0.65. I'm trying to erase. Sorry, guys. I'm trying to erase my, there we go. Erase my pen. There we go. So we're just going to take that area equals length times width, and we plugged it in here. Area is 0.65. That's given. Our length, we have no idea what the length is. The length is whatever the difference is between these two numbers. So we're going to plug that in here. X minus 0, which is just X. Okay. It's going to be our length is X. Our width, or the height, is 1/4. Okay. Because we know it goes from 0 to 4. So you end up simplifying the equation. 0.65 is equal to X divided by 4. We multiply both sides by 4 to get X is 2.6. So the number 2.6 is at the 65th percentile, meaning all the numbers below 2.6 represent 65% of the data, and all the numbers above represent 35%. Okay. Now, let's talk about the density curve and the normal distribution. Okay, we're going back to what is the shape of a distribution. Okay, both of these represent unimodal. It has one mountain. Okay, uni means one mountain. If it had 2 peaks, we'd call it bimodal. 3 peaks, you could call it trimodal, but usually after 2, we go to multimodal. Now, both of these are unimodal. The one over here to the left, this one, we would say it's skewed left because it's the tail is going to the left, okay? Over here, we would say it's skewed right because the tail is going to the right. Looks like somebody grabbed the data and pulled it to the right, okay? Now, this one in the middle, this is roughly symmetric, okay? It looks like we could fold it on itself, but it's got 2 mountains, so this is bimodal, okay? 2 mountains here, so this would be bimodal. Okay, now, our measures of center, we got mean and median, measures of center, okay? Variability, we got range, standard deviation, okay? These are going to apply to density curves as well as the distributions of quantitative data, okay? Now, the mean is the average, okay? It's in the middle, but it can also be referred to as the balance point. So if we were in a science class, okay, where you've got the fulcrum, where does that fulcrum need to be so that it balances? You can see this. We want it to be balanced. And again, just putting it in the middle doesn't work. Okay, moving it over right underneath it doesn't work. We want it to be perfectly balanced. So this is where our mean is. Okay, and again, we're putting our numbers in StatMedic and we're letting it spit out the mean for us. Let's just be real. Okay. Now, the median of the distribution is just going to be the point in the middle where if there's 100 pieces of data, we got 50 to the left and 50 to the right. Okay. Now, the median of a density curve is also the same thing. We want half of the area on each side. And again, if we look at the one on the left, median's kind of harder to pick out. But if we look at the one on the right, it's symmetric. Boom, it's in the middle. We can fold it in half and there's going to be our median. What's interesting is this would also be our mean because it's symmetrical. Yeah. They'll jump in a little ahead there, but when it's perfectly symmetrical, the mean and the median are the same thing. So you just need to know when it comes to a density curve, the mean is the point at which it would balance, like that slide we saw before, where it's going to balance perfectly, okay, if it was made of solid material. The median is simply going to be where you've got an equal amount of area on the right and the left, okay? Now, I just talked about this. This is where we're getting into a normal distribution. A normal distribution is going to look like this. It's going to look like a bell, okay? And when we have it where both sides are identical, it's going to balance perfectly in the middle. I mean, you literally could take it and fold it in half and that crease, boom, there's your mean. And again, when it's symmetrical, the mean and the median are what? The exact same. Okay, mean and median are the same. Oops, I'm pushing the wrong button. Okay, so it's really, if it's a skewed density curve, it's kind of hard to spot where the mean or the median is. But when it's symmetrical like this, again, yeah, it's just in the middle. And this is why we like these normal distributions. We're going to be dealing with normal distributions a lot because this is what a normal distribution looks like. When it's skewed, it's a whole lot harder to find the mean and the median. And again, when they're skewed, they're not the same thing. But really, pay close attention. The mean and the median are the exact same when it's normally distributed. Okay. Now, okay, if it's left skewed, here's part of what you need to know. Okay. So this is kind of where we'll go when it's not perfectly symmetrical. You need to know, like, where is the mean going to be relative to the median, because they're not the same. If it's symmetrical, they're the same. But when they're not symmetrical, you might have the mean further to the right, the medians to the left, or the other way around. Okay. So here, let's look at this. This one's obviously skewed left. Okay. So we want to identify the mean and the median just by the letter. Okay. Now, since this is left skewed, this is not going to be my median because C is directly under that peak. Okay. That cannot be the median. Okay. C, it just can't. Okay. So the one directly under the peak, I immediately go, yeah, that's neither one. Now, the median you see here in our answer, B is our median and the mean is A. So when it is left skewed, the tail's going out to the left, that means our mean is going to also be to the left of the median. Okay, you just need to memorize that. The mean will be left of the median when it's left skewed. What do you think is going to happen if it's right skewed? If it's right skewed, the mean is going to be to the right of it. Okay. Now, let's talk about the mean. We're going to now label it. You've seen me do this. We are going to label it as mu. This is lowercase mu. We've talked about this one too, just because you've seen it in your calculators. This is lowercase sigma. Mu starts with an M, it's mean. Sigma starts with an S, it's standard deviation. Okay. So let's go back to this density curve where we made it a rectangle. Okay. Oops. When we examine a distribution of quantitative data, how does it compare with an idealized density curve? So when we did this density curve to make it simpler, our results were pretty close. We were 0.2 off. And again, this isn't life or death situation where that 0.2 could affect someone's life. No, it's just us making a decision. Are we going to walk or ride the train? Okay. Now here we've got a histogram. Okay. And does this look roughly symmetrical? It does. Now, nothing's ever going to be perfectly. It looks roughly symmetrical. We would call this a normal distribution. Okay. So here we've got these state tests, EOCs, whatever you want to call them. Okay. We see there's no gaps, roughly symmetric. Both tails fall off smoothly from a center peak. Okay. This is called a normal curve because you can see there, it looks like a bell and it pretty much follows that pattern. This is what we like in statistics. We like normal curves. Okay. Because if it is a normal curve, there's a lot of stuff we can do, especially in StatMedic. Okay. Now, these normal curves, we're going to call normal distributions, where most of the data is right in the center and it tapers off like a bell. Now, your normal distributions can look different. We can have a really flat bell like this one, or we could have a tall and skinny bell. They're both normally distributed, though, because they are roughly symmetrical and look like a bell. Okay, so part of normal distributions, and I've been saying this, the overall shape looks like a bell, single peaked, roughly symmetrical. Okay, the center, the mean, we're going to start calling it mu, is located right in the middle. Okay, it's going to be symmetrical and it's going to be the exact same as the median. That's why we like these. Okay, variability. We're going to use standard deviation as a measure of variability of a normal distribution. So if you look here on both of these, we would say that this point right here is 1 standard deviation above the mean. Same thing here. This point is 1 standard deviation above the mean. Now, what is that standard deviation? I don't know. I just can tell you that point is 1 standard deviation above the mean. Okay. Now, we can estimate standard deviation by eye on a normal density curve. And here's how. Okay. This is kind of an interesting concept. You are snow skiing. Okay. We're skiing down this mountain that's normally distributed. First, we're going to descend, okay, at an increasingly steep angle as you go out from the peak. But then there's going to become a point where, things start to flatten out rather than get steeper. So you start and you go steep, and then it'll start to flatten out. Where it starts to flatten out, that is going to be your standard deviation. Okay, so you can see here, oh, it goes steep, 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 steep. Now, if we look slope-wise, it looks like the slope is getting less and less right about there. So we would say that is 1 standard deviation. And again, the key there is we're estimating it, okay? We're just estimating. It's about right there. So what's the definition of a normal curve? A normal distribution, okay, it is described by a single symmetrical bell-shaped curve. We're going to call that a normal curve. Okay. And when we talk about normal distributions, mean is going to be mu and standard deviation is sigma. And the reason we do this is if I see this written down, I know it's a normal distribution. Okay. So let's look here at these standardized test scores. Given information here, boom, you always want to look, see what's given. And I like to put a box around it. They're telling me the mean is 6.84 with a standard deviation of 1.55. We can find this out if we knew all the test scores. We put it in StatMedic. They did it for us. Yay, love that. Okay. So I can draw this normal distribution. I know it's single peaked, bell-shaped, symmetrical. And I know that the center, the median, and the mean is going to be 6.84. And then to find these numbers here, the 3 on the left and the 3 on the right, all I'm going to do is 6.84 plus 1.55. And then I get 8.39. If I take 8.39 and I add the 1.55 to it, I get 9.94. If I take the 9.94 and add 1.55 to it, I get 11.49. And I do the same thing over on this side. 6.84 minus 1.55 gives me 5.29, and so on. Okay. And you can see this is 1 standard deviation. This would be 2 standard deviations above the mean. And this would be 3 standard deviations above the mean. And we would do the same thing over here. I'd have 1 standard deviation below the mean. 2 standard deviations below the mean is 3.74, and 3 standard deviations below the mean is 2.19. Okay. So to get the top numbers, we add. To get the bottom numbers, we subtract. Okay. So let's look at our example here. We're going to talk about batting averages. Okay. So we're going to talk about how many times the player gets a hit out of the total number of times at bat. And these are real baseball stats, y'all. Okay, so we're going to look at Major League Baseball players that had at least 100 plate appearances, and that can be modeled by a normal distribution. How do I know? Because it's telling me. That is huge. When you do your homework, you want to see it say it's normally distributed. Okay, so it's giving me the mean. You'll mark those. It's giving me the standard deviation. I'd be writing it out on my sheet of paper. I would have a notebook, and on every one, I'd be like, oh, mean is 0.261, standard deviation 0.034. So I can look at it and know that's given data. Okay. We're going to sketch the normal density curve. Well, we know that the normal density curve is going to be single peaked, bell-shaped. Yours might be flatter than this. Yours might be taller. Doesn't matter, okay? We're just going to roughly draw it. We know that the mean is in the middle. So we're going to put that mean right there, 0.21. And then I'm just going to take my calculator, 0.21. And I'm going to find that standard deviation, 0.034. I'm going to go 0.261 plus 0.034. I get 2.95. Plus 0.034. And I'm going to get the 0.329. Plus 0.034. And now I'm going to get this final one here. And I'm going to repeat that, 0.021, and I'm going to get this side by going minus 0.034. I get 0.227. Minus 0.034, 0.193. Minus 0.034, 0.159. Okay? So pretty simple math here. Okay? Now, we need to make sure that we understand that the mean, mu, and lowercase sigma, standard deviation, do not specify the appearance of most distributions, okay? The shape of density curves in general does not reveal standard deviations. These are specifically to normal distributions because that density curve is a rectangle. When we're talking about a normal distribution, it's bell-shaped. So two completely different shapes, okay? So let's check our understanding. Should you be able to use that density curve, the rectangle, to model a distribution of quantitative data? Yes, can. We can get a good approximation. Can we identify the relative locations of the mean and median in that density curve, in that rectangle? Where's your mean at and where is your median at? And then if it's normally distributed, can we draw that bell-shaped, single peak bell shape to model the distribution? And not only that, we know the mean and median is in the middle. And if we're given the standard deviation, we should be able to add that standard deviation and get 1 standard deviation, 2, and 3. It's very important that you make sure you get that and subtract it. Because when we go to the next lesson, you're going to find 64% of your data is within 1 standard deviation above and below the mean. 95% is within 2 standard deviations, and 99.7 is within 3 standard deviations. That's what's the beauty. This is what's going to come from this normally distributed, okay? Is that 99.7% of our data is going to be within 3 standard deviations of the mean. Yeah, got some outliers. Could have some outliers there in that 0.03, but that's where we're headed. All right, so you have got lesson 2.3 keyed, and have fun. I'll see you tomorrow.